We build rockets, we clone animals, we have AI, and we still cannot figure out what a Roman builder knew 2,000 years ago. The Coliseum should be rubble by now. It is not. Modern concrete crumbles within decades. Roman concrete literally heals itself. Scientists have spent years trying to copy it and failed every single time. Then last week, a team from MIT cracked open a sample of ancient concrete and found something inside that nobody expected. Something that has been staring researchers in the face for years. The answer was there the whole time, and it changes everything. If you walk through Rome today and stand in front of the Coliseum, you are looking at a structure that has been there for nearly 2,000 years. It is cracked in places, worn by centuries of weather and earthquake activity, and large sections of it were stripped of their original stone facing long ago. And yet structurally it is still standing. The same is true for the Pantheon, which was completed around 128 AD and still holds the record as the world's largest unreinforced concrete dome. Both of these buildings have survived wars, neglect, natural disasters, and the slow grind of time in a way that is genuinely difficult to explain when you compare them to many modern structures that begin to show serious deterioration within a matter of decades. That comparison is worth sitting with for a moment. We live in an era of advanced engineering software, precision manufacturing, and materials science that would be completely unrecognizable to a Roman builder. And yet the concrete those builders used has, in many cases, outlasted what we produce today. That raises an obvious and somewhat uncomfortable question. What did they know that we do not? The short answer is that for a very long time we did not know what they knew. The methods the Romans used to produce their concrete were not passed down in any complete or usable form. Knowledge of the specific manufacturing process faded over. The centuries following the decline of the Western Roman Empire, and by the medieval period, it had effectively been lost. Researchers, architects, and material scientists have been trying to piece it back together ever since, with limited success. Modern attempts to replicate Roman concrete have consistently fallen short, producing materials that do not behave in the same way and certainly do not last as long. What makes this especially striking is that Roman concrete was not just durable in the ordinary sense. It had properties that go well beyond what we typically expect from a building material. One of the most significant of these is that it was capable of setting and hardening underwater. That might not sound remarkable at first, but it is an unusual property that opened up a range of construction possibilities that would otherwise have been impossible. Because of it, the Romans were able to build directly into the sea, constructing harbours, breakwaters, and piers that extended out into open water. These were not small or temporary structures. Some of them were enormous engineering projects that served major ports across the Roman world for centuries. Beyond that, Roman concrete has demonstrated something even more unusual. It appears to have the ability to heal itself. Small cracks that form in the material do not simply remain and widen over time the way they would in modern concrete. Instead, something within the material responds to those cracks and fills them in. The result is a substance that, under the right conditions, actually becomes stronger as it ages rather than weaker. That is essentially the opposite of how modern concrete behaves, and it is one of the central reasons why researchers have been so determined to understand how Roman concrete works. Much of what we know about how Roman concrete was supposed to be made comes from ancient written sources. The Romans were not secretive about their construction methods, at least not in a formal sense. Writers and engineers of the time documented the materials they used and the standards they held themselves to. One of the most important of these sources is Vitruvius, a Roman architect and engineer who was active during the 1st century BC. His written works cover a wide range of subjects related to architecture and engineering, and they include detailed descriptions of the ingredients that went into Roman concrete and where those ingredients should come from. According to accounts like those left by Vitruvius, the core ingredients of Roman concrete were water, limestone, volcanic ash, and rock fragments. But the specifications did not stop at simply listing what to use. There were strict requirements about quality and sourcing. The limestone, for example, had to be pure white, free from impurities. The volcanic ash, which was one of the most critical ingredients, was specified to come from a particular region around the Bay of Naples. This specific ash was considered so important to the concrete mixture that it was transported across the Roman Empire to be used in construction projects far from its source. Ancient writers described it as a key ingredient, something that could not simply be substituted with whatever volcanic material happened to be locally available. The significance of that volcanic ash became clearer through a study published in 2017 by researchers at the University of Utah. That team focused their attention on Roman concrete structures that had been submerged in the ocean, specifically the remains of piers and breakwaters that once made up working Roman harbors. These structures had been described in ancient texts by Pliny the Elder, a Roman natural philosopher and military commander, who wrote that they were impregnable to the waves and grew stronger with every passing day. That description, which might easily be dismissed as poetic exaggeration, turned out to be more accurate than anyone had anticipated. When the research team analyzed samples taken from these submerged structures, they found deposits of a mineral called aluminous tobermorite. This is a rare substance that is extremely difficult to produce under normal conditions, and it almost certainly was not present in the concrete when it was first poured. What the researchers found was that over time, as small cracks formed in the material, seawater seeped into those cracks and triggered a low-temperature chemical reaction between the salt water and the volcanic ash crystals already present in the concrete. That reaction produced crystals of aluminous tobermorite, which filled the cracks and reinforced the surrounding material. The concrete was not just surviving contact with seawater, it was using that contact to repair and strengthen itself. That finding went a long way toward explaining why Roman marine structures had held up so well, but it left some questions unanswered. The self-healing mechanism identified in those submerged structures depended on the presence of seawater. What about Roman concrete structures built on land, far from the sea? Many of those had also survived for extraordinary lengths of time, and the same mechanism could not straightforwardly account for that. And the deeper question of the exact recipe and manufacturing process still had not been resolved. Modern researchers who had tried to recreate Roman concrete using the known ingredients kept arriving at results that failed to match the original. Something in the process was still missing. One clue had been sitting in plain sight for years without being properly understood. Researchers examining samples of ancient Roman concrete collected from sites across the former empire kept noticing the same thing. Scattered throughout practically every sample were small, bright white mineral features, roughly a millimeter in size. These white clusters came from the limestone used in the manufacturing process and had been given the name limeclasts. For a long time, the prevailing assumption among researchers was that these clasts were simply the result of careless or incomplete mixing. The idea was that the Romans had not done a thorough enough job of combining their ingredients, and these little white flecks were the evidence of that oversight. That explanation never quite sat right. Everything else known about Roman concrete production pointed to an operation that took quality seriously. The sourcing requirements were strict, the ingredient specifications were detailed, and the accounts left by ancient writers suggest a culture of careful attention to materials. It seemed inconsistent that a civilization which went to that much trouble selecting and transporting the right volcanic ash from the right location around the Bay of Naples would then produce their final product through sloppy mixing. There was a reasonable case to be made that these limeclasts were not a mistake at all, but a feature, and that understanding what they were doing there was the key to unlocking the whole mystery. To understand what those limeclasts were actually doing in Roman concrete, it helps to understand a little about limestone and what happens to it when it is processed. Limestone quarried from the ground is not used directly in concrete production. It has to be heated first, typically in a kiln, at very high temperatures. When limestone is burned in this way, it produces a material called quicklime. Quicklime has been used by humans for thousands of years across a wide range of applications. It plays a role in plaster and cement production, in steel making, and in paper manufacturing. It also has an unusual property that was once used in theatre before electric lighting existed. When quicklime is heated above a certain temperature, it emits a bright, intense white light. This was used to illuminate performers on stage, and it is where the phrase "in the limelight" comes from. When quicklime is combined with water, a process known as slaking, it produces a highly reactive paste-like material and releases a significant amount of thermal energy in the process. The product of slaking is calcium hydroxide, which is also called slaked lime or hydrated lime. For a long time, the assumption among researchers trying to decode Roman concrete was that this was the form in which lime entered the mixture. The thinking was that the Romans would have slaked their quicklime first, producing that reactive paste, and then incorporated it into the rest of the concrete ingredients. That was the standard interpretation, and it seemed reasonable enough on the surface. The research team, led by Admir Masick at MIT, began to question whether that assumption was correct. Their focus kept returning to those small white lime clasts that appeared throughout Roman concrete samples. If the lime had been fully slaked before being added to the mixture, it was difficult to explain how those clasts had formed in the way they had. Slaking is a thorough process. It hydrates the quicklime completely, and the result should not leave behind the kind of distinct, localized white clusters that were showing up so consistently in the ancient samples. Something about the standard explanation did not add up. To get a clearer picture, the team carried out spectroscopic examinations of the lime clasts themselves. What they found was a hydration gradient within the clasts, with an outer layer that had been hydrated and an inner core that had not. That structure pointed strongly toward a very specific set of conditions during formation. The clasts appeared to have formed under extremely high temperatures, hotter than the slaking process alone would generate. This was an important observation because it suggested that the lime had not been fully processed into calcium hydroxide before it entered the mix. Instead, it looked as though quicklime had been added directly into the concrete in its dry, unhydrated form, and the intense heat had been generated within the mixture itself as the hydration took place on the spot. This process is known as hot mixing. Rather than slaking the quicklime separately in advance and then incorporating the resulting paste, hot mixing involves adding the quicklime directly to the other ingredients and allowing the hydration to occur as part of the mixing process itself. When calcium oxide, which is the chemical name for quicklime, hydrates in this way, it releases heat in what is called an exothermic reaction. The temperature increase within the mortar during hot mixing can be as much as 55 to 60 degrees centigrade above ambient conditions. And within localized hotspots in the mixture, temperatures could exceed 200 degrees centigrade. That is an intense amount of heat to be generated inside a building material, and it has significant consequences for how the material behaves both during production and over the course of its lifetime. One of the immediate practical benefits of hot mixing would have been a dramatic reduction in curing and setting time. When all the chemical reactions involved in concrete production are accelerated by that level of heat, the material hardens much more quickly than it would under normal conditions. For a society carrying out large-scale construction projects across a vast empire, a faster setting time would have been a meaningful advantage. It would have allowed work to proceed more quickly and reduced the time that newly poured structures needed to be supported and protected before they could bear loads. But the more significant consequence of hot mixing was what it left behind inside the concrete. The intense temperatures reached during the process gave the lime clasts a characteristically brittle structure at the nanoscale. Rather than being fully integrated into the surrounding material, they remained as distinct, reactive deposits scattered throughout the concrete, with a high surface area relative to their size. That brittleness was not a weakness. It was precisely what made the self-healing mechanism possible. As a concrete structure aged and was subjected to the ordinary stresses of settlement, temperature change, and physical load, tiny cracks would begin to form within the material. Those cracks, following the path of least resistance through the concrete, would tend to travel through the weaker lime clasts rather than through the harder surrounding matrix. When water later made its way into those fine cracks, it came into contact with the reactive calcium-rich material of the clasts. That contact triggered a chemical reaction. The water and the lime clast material together produced a calcium-saturated solution, which could then recrystallize into calcium carbonate, effectively filling the crack from within. In some cases, the water also reacted with volcanic ash components in the surrounding concrete, producing additional mineral growth that further strengthened the repaired area. The picture that emerged from this analysis was of a concrete that had been engineered, whether intentionally or through accumulated practical knowledge, to respond to damage rather than simply succumb to it. The lime clasts were not errors. They were a built-in repair system, activated by the very thing that causes damage in the first place. That is a remarkably sophisticated property for a material produced 2,000 years ago, and it reframed the entire history of how researchers had been thinking about Roman concrete. Having developed this hypothesis, the team needed to test it. A compelling theoretical explanation is one thing, but material science ultimately requires experimental evidence. The researchers set about producing their own concrete samples using the hot mixing method, incorporating both ancient-style ingredients and modern equivalents to see whether the process would produce the same lime clasts observed in the historical samples. Alongside these hot mix samples, they also prepared a set of control samples using the conventional approach in which quicklime was not added directly, but was instead processed in the standard way before being incorporated into the mix. The results of that first stage of testing were straightforward and encouraging. The hot mixed concrete samples contained clearly visible lime clasts distributed throughout the material, closely matching what had been observed in ancient Roman concrete samples collected from sites across the former empire. The control samples, which had not included quicklime in the hot mixing process, showed none of these clasts. That was a strong indicator that hot mixing was indeed the mechanism responsible for the lime clasts in the original Roman material, and it gave the team confidence that they were on the right track. The second stage of the experiment was designed to test the self-healing claim directly, which was ultimately the most important property that the whole theory was trying to explain. The researchers took each of their concrete columns, both the hot mix samples and the controls, and split them down the middle. The two halves of each column were then placed back together with a gap of approximately 1 millimeter between them, and a pump system was set up to push water continuously through that gap in each sample. The question was simple. Would the hot mixed concrete, with its lime clasts intact and reactive, be able to seal that crack on its own? Within a few weeks, something notable happened. The pump system attached to the hot mixed concrete sample shut itself off automatically. The water had stopped flowing. The crack had closed. A final spectroscopic analysis of the sealed area confirmed the presence of calcium carbonate, the same material produced when water reacts with the lime clasts, filling and healing the gap from within. The control samples without quicklime and therefore without lime clasts continued to run throughout the testing period. Water kept flowing through them, and they never repaired themselves. That result provided strong and direct experimental support for the hypothesis. The lime clasts were the mechanism. Hot mixing was the process that created them. And together, those two things explained a property of Roman concrete that had puzzled researchers for years and that no modern replication attempt had managed to reproduce. The mystery of why Roman concrete behaved so differently from anything produced since had, at least in its essential outline, been solved. There is a saying that is sometimes attributed to engineering circles, though its exact origin is difficult to pin down, which goes something like this. Anyone can build a bridge that stands, but only an engineer can build a bridge that barely stands. The point behind it is that good engineering is not simply about making something that works. It is about making something that works using the minimum amount of material, the minimum amount of energy, and the minimum amount of cost, while still meeting every requirement it needs to meet. That balance is genuinely difficult to strike, and the history of construction is full of examples where the pursuit of efficiency has come at the expense of longevity, and where the pursuit of longevity has come at an enormous cost to resources and the environment. Modern concrete is a good example of that tension. It is one of the most widely used construction materials on the planet. It is strong, it is relatively cheap to produce, it can be shaped into almost any form, and it sets quickly enough to support fast-paced construction schedules. In many respects, it is a practical and effective material, but it has a significant weakness, which is that it does not last. Compared to the Roman structures discussed earlier, modern concrete deteriorates at a rate that is almost embarrassing. Bridges, tunnels, buildings, and infrastructure of all kinds require regular maintenance, repair, and in many cases complete replacement within timescales that would have seemed extraordinarily short to a Roman engineer. That constant cycle of repair and replacement has consequences that go well beyond the financial. The production of cement, which is the binding ingredient that gives concrete its strength and cohesion, is one of the more significant contributors to global carbon dioxide emissions. Current estimates place the cement industry's share of global CO2 output at around 8%. To put that in perspective, that figure is comparable to the emissions produced by the entire aviation industry, and in some calculations, it exceeds it. The sheer scale of concrete use around the world means that even relatively modest improvements in the durability and lifespan of concrete structures could translate into a meaningful reduction in the total amount of cement that needs to be produced. If structures last longer, fewer of them need to be replaced. If fewer structures need to be replaced, less concrete needs to be made. And if less concrete needs to be made, less cement needs to be produced, with all the emissions that process involves. This is where the findings about Roman concrete move from being historically interesting to being practically important. The self-healing properties identified in ancient Roman concrete are not just a curiosity about how people built things 2,000 years ago. They represent a potential model for how concrete could be made differently in the future, in a way that addresses one of the more persistent problems in modern construction. A concrete that can repair its own small cracks as they form would require far less maintenance over its lifetime. It would be less likely to develop the kind of progressive structural deterioration that leads to costly repairs or full replacement. And if it could achieve that through a manufacturing process that uses less energy and produces fewer emissions than current methods, the environmental case for pursuing it becomes even stronger. The research team at MIT, having demonstrated through their experiments that hot mixing with quicklime produces concrete with genuine self-healing properties, did not treat that discovery as the end of the process. The gap between a laboratory finding and a material that can be used at scale in real construction projects is wide, and crossing it requires sustained collaboration between researchers and the industries that actually produce and use building materials. The MIT team has already begun working with industry groups to explore how the insights from this research can be translated into practical applications. That work is ongoing, and it is too early to say with certainty what form any resulting materials will take or how quickly they might become available for widespread use. But the direction of travel is clear, and the motivation for moving in that direction is strong. It is worth taking a moment to consider what it means that this discovery was made at all, and why it took as long as it did. The lime clasts that turned out to be the key to understanding Roman concrete's self-healing mechanism had been observed by researchers for years before their significance was recognized. They were present in practically every sample of ancient Roman concrete ever analyzed. They were visible to the naked eye. And for a long time, the working assumption was that they represented a quality control failure, a sign that the Romans had not mixed their ingredients thoroughly enough. That assumption was not unreasonable, given what was known at the time, but it turned out to be wrong, and its persistence delayed a correct understanding of the material by some years. That is not a criticism of the researchers who held that assumption. Science regularly proceeds by testing and revising its working models, and the eventual correction of a mistaken interpretation is exactly how the process is supposed to work. But it does illustrate something worth keeping in mind when thinking about ancient technologies and the people who developed them. There is a tendency, perhaps natural and understandable, to assume that earlier civilizations were working with a simpler and less sophisticated understanding of the world than we are today. In many areas, that is clearly true. But in some areas, particularly those involving practical and accumulated knowledge developed through generations of direct observation and experimentation, that assumption can lead researchers astray. The Romans did not have spectroscopic analysis or electron microscopy, but they had centuries of practical experience with their materials, and the concrete they produced as a result of that experience has properties that materials scientists are still working to fully replicate and understand. The question of how that knowledge was lost in the first place is also worth considering briefly. The fall of the Western Roman Empire in the 5th century AD was not a single event, but a prolonged process of fragmentation, economic decline, and political instability that unfolded over many decades. Large-scale infrastructure projects of the kind that had driven the development and refinement of Roman concrete became increasingly rare as the empire contracted. The networks of trade and supply that had made it possible to transport specialized volcanic ash from the Bay of Naples to construction sites across the empire broke down. The institutional knowledge that had been held by engineers and builders was not systematically recorded in a way that survived the disruption of the period that followed. Over time, the specific details of how Roman concrete was produced simply ceased to be known. What remained were the structures themselves, and the incomplete accounts left by writers like Vitruvius, which described what went into the material, but not, as it turned out, all of the details of how it was processed. That loss of knowledge is a reminder that even well-documented technical achievements can be fragile in the face of broader social and economic change. It also gives the recent research findings an added layer of significance. What the MIT-led team has done is not simply advance the scientific understanding of a historical material. They have recovered, through careful and methodical investigation, a piece of practical knowledge that was lost for over 1,000 years and demonstrated that it has direct relevance to some of the most pressing challenges in construction and environmental sustainability today. The broader implications of this kind of research extend beyond concrete specifically. There is a growing field of study focused on what might loosely be called bio-inspired or historically inspired materials, drawing on examples from nature and from human history to develop new approaches to engineering challenges. Roman concrete is one of the more compelling case studies in that area, precisely because its properties are so well documented through surviving structures that have been studied for decades, and because the gap between its performance and that of modern equivalents is so stark and so well established. It provides a concrete, in both senses of the word, example of what can be achieved when a material is designed, even if only through accumulated practical wisdom rather than formal scientific understanding, to work with the processes of degradation rather than simply against them. Whether the specific approach used by the Romans, hot mixing with quicklime to produce reactive limeclasts within the concrete matrix, can be adapted and scaled for use in modern construction, remains a question that will be answered over the coming years as industry collaboration continues and further research is carried out. The early results are genuinely promising, and the experimental evidence produced by the MIT team provides a solid foundation to build on. The challenge now is an engineering and industrial one as much as a scientific one, involving questions of cost, scalability, and compatibility with existing construction practices that go beyond what a laboratory experiment can resolve. What is already clear, however, is that the assumption which underpinned decades of research into Roman concrete, the assumption that the limeclasts were a flaw, was mistaken, and that correcting that mistake has opened up a new and productive line of inquiry with real practical potential. Sometimes the most important discoveries are not the result of looking in a new place, but of looking at something familiar in a different way. The limeclasts were always there. They just needed someone to ask the right question about them.